There are places in the universe where darkness is not simply the absence of light. It is a force, a boundary, a silence so complete that even the fastest thing in existence cannot escape it. A black hole is not a hole in the ordinary sense. It is not an empty tunnel through space. It is a region where gravity has become so intense that space and time themselves are bent into a one-way path. Cross its outer boundary, and every possible future leads inward. For centuries, black holes belonged more to mathematics than to astronomy. They were predictions written in equations, strange consequences of gravity carried to its limit. They sounded impossible, a place where light cannot escape, a point where density becomes infinite. A cosmic object that can be detected only by what it does to everything around it. And yet, black holes are real. We have watched stars race around an invisible mass at the center of the Milky Way. We have detected ripples in space-time from black holes colliding more than 1 billion years ago. We have seen the glowing ring of superheated gas around the shadow of a black hole in another galaxy. The first direct image of a black hole's surroundings came from the Event Horizon Telescope in 2019, showing the supermassive black hole in the galaxy M87. In 2022, the same global telescope network revealed Sagittarius, a star, the black hole at the center of our own galaxy. But every answer has only deepened the mystery. Black holes sit at the meeting point of the two greatest theories in physics. General relativity describes gravity as the bending of space-time. Quantum mechanics describes the strange behavior of matter and energy at the smallest scales. Both theories have been tested with astonishing success. Both are pillars of modern science. But inside a black hole, and especially near its deepest center, they appear to collide. This is why black holes are not only astronomical objects, they are questions. They ask what space really is. They ask what time really means. They ask whether information can be destroyed. They ask whether the universe is predictable at its most fundamental level. They ask what happens when the laws of nature are pushed beyond the edge of everything we can observe. And among all the mysteries of black holes, one idea may be the most haunting. In the 1970s, Stephen Hawking discovered that black holes should not be completely black. When quantum theory is applied near the event horizon, a black hole should emit a faint thermal glow. Over immense spans of time, this radiation should drain energy from the black hole, slowly causing it to shrink. This is Hawking radiation. It has never been directly observed from an astrophysical black hole, because for large black holes, the effect is incredibly weak. But the theory transformed black holes from cosmic prisons into objects with temperature, entropy, and perhaps a final death. The darkest objects in the universe may evaporate, and if they evaporate, they leave behind a question that has troubled physics for half a century. What happens to everything that fell in? Long before black holes had a name, scientists imagined stars so massive that their gravity could trap light. In the late 18th century, the English clergyman and natural philosopher John Michell considered a simple idea. If a cannonball fired from Earth must reach a certain speed to escape Earth's gravity, then perhaps light itself might also fail to escape a sufficiently massive star. Pierre-Simon Laplace later explored a similar possibility. These hypothetical objects were sometimes called dark stars. At the time, light was still often imagined as a stream of particles. Gravity was described by Newton's laws. The idea was bold, but it was not yet a black hole in the modern sense. It was not a region where space-time curved into a trap. It was a massive object whose escape velocity exceeded the speed of light. The true black hole would require a new understanding of gravity. That came in 1915, when Albert Einstein presented general relativity. In Einstein's universe, gravity is not simply a force pulling objects through space. Gravity is geometry. Matter and energy curve space-time, and objects follow the paths that curved space-time allows. A planet orbits the Sun, not because the Sun reaches out with an invisible rope, but because the Sun bends the space-time around it. Earth follows that curvature. Light, too, follows the shape of space-time. This means gravity can bend light, slow time, and reshape the structure of the universe. Only weeks after Einstein's theory was published, Carl Schwarzschild found an exact solution to Einstein's equations for the gravitational field outside a spherical mass. Hidden inside that solution was a strange radius. If the mass were compressed within this radius, the escape velocity would equal the speed of light. Today, that radius is called the Schwarzschild radius. For the Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it is less than a centimeter. If either object could be crushed within that size, it would become a black hole. At first, many physicists did not believe such objects could exist in nature. The mathematics seemed to produce a strange boundary, but perhaps the real universe would prevent matter from collapsing so far. Einstein himself did not embrace black holes as physical objects. They appeared too extreme, too pathological, too close to a breakdown of the theory. But stars do die. A star survives by balancing gravity against pressure. For most of its life, a star shines because nuclear fusion in its core releases energy. That energy pushes outward while gravity pulls inward. The star is a battle held in equilibrium. When the fuel runs out, the balance changes. Smaller stars can become white dwarfs. Heavier stars may collapse into neutron stars, where matter is crushed to densities beyond anything on Earth. But if enough mass remains after the collapse, no known pressure can stop gravity. The star falls inward. In 1939, J. Robert Oppenheimer and Hartland Snyder calculated the gravitational collapse of a massive star under general relativity. Their work showed that continued collapse could form what we now call a black hole. To an outside observer, the star's surface would appear to slow as it approached the critical boundary. Its light would stretch toward redder and redder wavelengths. It would fade. But for the collapsing matter itself, the fall would continue. The term black hole would not become popular until the 1960s, when physicist John Wheeler helped give the object its memorable name. By then, black holes were no longer dismissed as mathematical curiosities. They were becoming unavoidable. Roger Penrose showed in 1965 that black hole formation was a robust prediction of general relativity. His singularity theorem demonstrated that, under realistic conditions, gravitational collapse could lead to a singularity, a place where the classical theory predicts spacetime curvature becomes infinite. The 2020 Nobel Prize in Physics recognized Penrose for showing that black hole formation is a direct consequence of general relativity, and Reinhard Genzel and Andrea Ghez for work showing that a supermassive compact object governs the orbits of stars at the center of the Milky Way. Black holes had moved from speculation to inevitability, but their name can be misleading. A black hole is not simply black. It is not simply a collapsed star. It is not merely an object. It is a region of space-time. Its defining feature is not the matter that formed it, but the boundary that surrounds it. That boundary is the event horizon. The event horizon is the surface of no return. It is not solid. You would not hit it like a wall. If the black hole were large enough, you might cross the horizon without noticing anything special in that instant. But after crossing it, escape would no longer be possible. Every direction that once might have led outward now leads deeper in. The reason is not that light becomes weak, or that engines fail, or that gravity merely pulls very hard. The reason is more profound. Inside the horizon, space-time is shaped so that the future points inward. To leave would require moving faster than light, and according to relativity, nothing can do that. The event horizon is therefore a boundary in causality. It divides the universe into what can still send signals to the outside and what cannot. Outside the horizon, the universe can watch, infer, measure, and theorize. Inside, whatever happens is hidden forever from external observers. This makes black holes unique. Most objects are understood by studying the light they emit or reflect. Black holes emit no ordinary light from within the horizon. They reveal themselves indirectly through gravity, motion, heat, radiation from nearby matter, and the waves they send through space-time when they collide. A black hole is visible only through its influence. It is the dark center of a luminous storm. To see a black hole, astronomers must look for what the black hole does. A solitary black hole drifting through empty space would be nearly impossible to detect. If no gas surrounds it, if no star orbits it, if no background light passes behind it, it may leave almost no visible trace. It would be a silent distortion moving through the galaxy. But many black holes do not live alone. Some are paired with stars. In these systems, the black hole can pull gas from its companion. The stolen gas does not fall straight in. It spirals, flattens, and forms an accretion disk, a rapidly rotating disk of matter heated by friction, compression, and magnetic turbulence. Near the black hole, this disk can glow across the electromagnetic spectrum, including X-rays. NASA describes accretion disks as a main light source around black holes, while isolated black holes without surrounding matter are much harder to find. The black hole itself remains dark. The light comes from matter still outside the horizon. This is one of the paradoxes of black holes. The darkest objects in the universe can power some of the brightest phenomena. Quasars, among the most luminous objects known, are driven by supermassive black holes feeding on large amounts of gas in the centers of galaxies. The energy does not come from the black hole shining. It comes from matter losing gravitational energy as it falls toward the hole. A black hole is a gravitational engine. As gas spirals inward, it can be heated to millions of degrees. Magnetic fields twist and amplify. Some material falls through the horizon, vanishing from view. Some may be launched outward in narrow jets moving at nearly the speed of light. These jets can extend far beyond the host galaxy, carrying energy into intergalactic space. The exact mechanism behind black hole jets remains an active field of research. The leading ideas involve magnetic fields, spinning black holes, and rotating accretion disks. Somehow, the region around the black hole organizes chaotic infalling matter into beams of extraordinary power. This is one way we detect black holes, by the light and radiation of matter around them. Another way is through motion. At the center of the Milky Way, visible light is blocked by dust. But infrared telescopes can peer through the galactic center and track the orbits of stars near a compact radio source called Sagittarius, a star. These stars move with astonishing speed. One star, known as S2 or SO2 depending on the naming convention, follows a tight elliptical orbit around something massive and invisible. The object at the center does not shine like a star. It is packed into a region smaller than our solar system. Its mass is about 4 million times the mass of the Sun. The only currently known explanation is a supermassive black hole. Nobel Prize material and later measurements identify Sagittarius, a star, as the compact object at our galaxy's center, with a mass of roughly 4 million solar masses. Here, black holes are not seen by light, they are weighed by gravity. A third method is gravitational lensing. Because mass curves space-time, a black hole can bend the path of light passing nearby. If a black hole moves in front of a distant star, the star's light may brighten and distort as the black hole's gravity acts like a lens. Such microlensing events can reveal isolated dark objects that would otherwise remain invisible. A fourth method arrived in 2015, when humanity detected gravitational waves directly for the first time. Gravitational waves are ripples in space-time produced by accelerating massive objects. Einstein's general relativity predicted them, but for decades they were known mainly through indirect evidence. Then the laser interferometer, gravitational, wave observatory known as LIGO detected a signal from two black holes spiraling together and merging. The black holes were about 29 and 36 times the mass of the Sun. About 3 solar masses were converted into gravitational wave energy in a fraction of a second. The event had taken place around 1.3 billion years earlier. For the first time, we did not see black holes, we heard them. The signal was a chirp, a rising tone produced as the black holes orbited faster and faster, then merged into one. The final black hole rang down like a struck bell, settling into a stable shape described by mass and spin. This discovery opened a new kind of astronomy. Telescopes collect light. Gravitational wave detectors listen to space-time itself. They can detect events that produce little or no light, including black hole mergers in the darkness between galaxies. And then, in 2019, came the image. The Event Horizon Telescope is not one telescope, but a global network of radio observatories working together as an Earth-sized instrument. By combining signals from telescopes across the planet, scientists achieved the resolution needed to study the immediate surroundings of a supermassive black hole. The target was the black hole in M87, a giant elliptical galaxy about 55 million light-years away. The image did not show the event horizon directly. It showed a bright ring of emission from hot gas near the black hole, surrounding a dark central shadow. That shadow was created by the black hole's gravity capturing light and bending the paths of photons around it. NASA describes the 2019 M87 image as the first picture of a black hole, outlined by emission from hot gas swirling near the event horizon. The image was blurry, orange, and historic. For generations, black holes had been equations, artist impressions, and indirect evidence. Now the world could see the silhouette of a black hole's gravity. But the image was not the end of the mystery. It was the beginning of a more precise one. The shadow matched the predictions of general relativity. The ring size matched expectations for a black hole of billions of solar masses. The universe, once again, seemed to obey Einstein in the most extreme conditions we could observe. And yet, Einstein's theory is not complete. General relativity can describe the event horizon, the orbits of stars, the bending of light, the merging of black holes, and the ripples that flow outward afterward. But at the singularity, the theory breaks down. It predicts its own failure. And when quantum effects are included near the horizon, the black hole is no longer perfectly black. This is where the visible mystery becomes invisible again. The event horizon is one of the most important ideas in modern physics. It is also one of the most misunderstood. In popular imagination, the event horizon is sometimes pictured as a physical surface, a dark shell, a membrane, a cosmic waterfall. But in classical general relativity, the horizon is not made of matter. It is a boundary in space-time. It is defined by light. Outside the horizon, a beam of light can, in principle, escape to distant space if it is aimed in the right direction. At the horizon, outward-directed light can hover only at the edge. Inside the horizon, even outward-directed light is carried inward. The escape speed is greater than light speed, and light cannot outrun spacetime's inward curve. NASA describes the event horizon as the boundary inside which the velocity needed to escape exceeds the speed of light, so whatever passes, it remains inside, even light. For a small black hole, crossing the horizon would be catastrophic long before the crossing. Tidal forces would stretch and compress matter violently. This effect is often called spaghettification. The gravity acting on the side of an object closer to the black hole can be much stronger than the gravity acting on the far side. The result is stretching in one direction and squeezing in others. But for a supermassive black hole, the horizon can be enormous. The tidal forces at the horizon may be gentle enough that an astronaut crossing it would not immediately feel anything unusual. Locally, there may be no flashing warning sign, no wall, no obvious edge. The danger is global, not local. Once inside, the future is changed. The simplest black hole is non-rotating and uncharged. It is called a Schwarzschild black hole, but real black holes almost certainly rotate. Stars rotate, gas disks rotate, mergers produce spin. A rotating black hole is described by the Kerr solution to Einstein's equations, named after Roy Kerr. Spin changes everything. Around a spinning black hole is a region called the ergosphere. In the ergosphere, space-time itself is dragged around by the rotation of the black hole. This effect is called frame dragging. An object inside the ergosphere cannot remain still relative to the distant universe. It must rotate with space-time. The ergosphere lies outside the event horizon at the equator of a rotating black hole. In principle, energy can be extracted from this region. This idea, known as the Penrose process, shows that a spinning black hole's rotational energy is not entirely locked away. Modern theories of jets often involve related processes in which magnetic fields help extract energy from spinning black holes and accretion disks. Then there is the photon sphere. For a non-rotating black hole, the photon sphere is a region where light can orbit the black hole. These orbits are unstable. A tiny disturbance sends photons either outward into space or inward toward the horizon. The photon sphere helps shape the black hole's shadow seen by the Event Horizon Telescope. A black hole's surroundings are therefore not simple darkness. They are structured by invisible surfaces and zones: the accretion disk, the photon sphere, the ergosphere, the event horizon, and deep within, the singularity predicted by classical theory. But the singularity is different. The event horizon is a boundary from which light cannot escape. The singularity is where general relativity says, curvature becomes infinite and known, physics loses meaning. In the Schwarzschild solution, the singularity is a point. In the Kerr solution, for a rotating black hole, it appears as a ring. But physicists do not generally believe that infinities are physical objects waiting inside the universe. An infinity usually signals that the theory has reached the limit of its domain. The singularity is not so much a destination as a warning. It tells us that general relativity, powerful as it is, cannot be the final word. At extremely small scales, quantum effects should matter. But we do not yet have a complete and tested theory of quantum gravity. This is the heart of the black hole mystery. General relativity is the theory of the very large, planets, stars, galaxies, space-time, the expanding universe. Quantum mechanics is the theory of the very small, particles, fields, probabilities, uncertainty. A black hole can be massive enough to curve space-time on cosmic scales, yet compact enough that its deepest interior demands quantum physics. Black holes force the universe's two rulebooks onto the same page, and the page does not yet make sense. Black holes are often imagined as destroyers. They consume stars, bend light, and trap anything that crosses their horizons. But in the larger story of the cosmos, black holes are not merely endings, they are engines. At the centers of many galaxies lie supermassive black holes. Their masses range from millions to billions of times the mass of the Sun. The Milky Way's central black hole is relatively quiet today, but in other galaxies, central black holes are actively feeding. Gas falls inward, forms hot disks, and releases enormous energy before crossing the event horizon. These active galactic nuclei can outshine the combined stars of their host galaxies. Quasars, powered by rapidly feeding supermassive black holes, can be seen across billions of light years. Their light began its journey when the universe was young. The power source is gravity. Nuclear fusion converts a small fraction of mass into energy. Accretion onto a black hole can be even more efficient. As matter spirals inward, gravitational energy becomes heat, radiation, and motion. The black hole itself does not need to shine. The environment around it becomes luminous. This process affects galaxies. Jets and winds from active black holes can heat surrounding gas, push material out of galactic centers, and influence star formation. In some cases, black hole activity may prevent gas from cooling enough to form new stars. In others, shocks and compression may help trigger star formation. The relationship is complex, but observations show that galaxies and their central black holes evolve together. There is a curious connection between the mass of a galaxy's central black hole and the properties of the galaxy's bulge, the dense central concentration of stars. This suggests feedback. Black holes grow with galaxies, and galaxies are shaped by black holes. A black hole, then, is not only a grave, it is part of cosmic ecology. But how did supermassive black holes become so large? This remains one of the great open questions. Stellar mass black holes can form from the collapse of massive stars. Intermediate mass black holes may form through mergers, dense star clusters, or other channels, but their population is still being investigated. Supermassive black holes may grow from smaller seeds by consuming gas and merging with other black holes. But astronomers have found very massive black holes in the early universe when there seems to have been limited time for growth. This raises possibilities. Perhaps the first stars were massive and left behind large black hole remnants. Perhaps some black holes formed by direct collapse of enormous gas clouds. Perhaps dense star clusters produced runaway mergers. Perhaps primordial black holes formed in the earliest moments after the Big Bang, from density fluctuations in the young universe. Primordial black holes remain hypothetical. No confirmed primordial black hole has been found. But the idea remains scientifically interesting because such objects could have formed without stars. Depending on their mass, they might also relate to dark matter, though observations have placed strong limits on many possible mass ranges. Black holes also grow through mergers. When two galaxies collide, their central black holes may eventually sink toward the combined center and form a binary. Over long timescales, they can spiral together and merge, releasing gravitational waves. Stellar mass black holes do the same in binary systems. LIGO and other detectors have now made gravitational wave astronomy a practical way to study black hole populations. Each merger is a message. The masses and spins of merging black holes reveal how they formed. Some may come from isolated binary stars. Others may come from dense clusters where black holes meet through gravitational interactions. Some black holes may be second-generation objects, formed from previous mergers and then merged again. The universe may be full of black holes with histories written in their spins. And yet black holes are simple, at least from the outside. According to the classical no-hair idea, a stable black hole is described by only a few properties: mass, electric charge, and angular momentum, or spin. In realistic astrophysical settings, charge is expected to neutralize quickly, leaving mainly mass and spin. A black hole formed from a star, from gas, from books, from planets, from anything at all, eventually settles into the same external form if those few properties are the same. This simplicity is both elegant and disturbing. Because if the outside of a black hole remembers only mass and spin, what happens to all the detailed information about what fell in? The answer leads directly to Hawking's discovery. In the early 1970s, black holes began to look less like cold mathematical traps and more like thermodynamic objects. Thermodynamics is the physics of heat, energy, and entropy. It describes why heat flows from hot objects to cold ones, why engines have limits, and why disorder tends to increase. At first glance, thermodynamics and black holes seem unrelated. A black hole, in classical general relativity, absorbs everything and emits nothing. It has no glow, no temperature, no visible surface. But several clues suggested a deeper connection. The area of a black hole's event horizon behaves strangely. In classical processes, the total area of black hole horizons does not decrease. If two black holes merge, the area of the final horizon is at least as large as the sum of the original horizon areas. This resembles the second law of thermodynamics, which says entropy tends not to decrease. Jacob Bekenstein took this resemblance seriously. He proposed that black holes have entropy, and that the entropy is proportional to the area of the event horizon, not the volume inside. This was radical. Entropy is usually associated with microscopic arrangements. If a black hole has entropy, then it must somehow have hidden microscopic states. Stephen Hawking initially resisted the idea. If a black hole has entropy, thermodynamics suggests it should also have a temperature, and if it has a temperature, it should radiate. But classical black holes do not radiate. Then Hawking did the calculation. He studied quantum fields in the curved space-time around a black hole. The result shocked even him. Black holes should emit radiation. Not because matter escapes from inside the horizon, but because the quantum vacuum near the black hole is affected by the horizon and the curvature of space-time. The radiation has a thermal spectrum. The black hole behaves like a body with a temperature. This temperature is inversely proportional to mass. The smaller the black hole, the hotter it is. The larger the black hole, the colder it is. A black hole with the mass of the Sun would have a temperature far below the temperature of the cosmic microwave background. A supermassive black hole would be colder still. That is why Hawking radiation from ordinary astrophysical black holes is expected to be far too faint for current direct detection. But the theoretical consequences are enormous. If a black hole radiates, it loses energy. Because energy and mass are equivalent, losing energy means losing mass. Over time, the black hole shrinks. As it shrinks, it gets hotter. As it gets hotter, it radiates faster. The process accelerates. For a stellar mass black hole, the timescale is almost unimaginable, vastly longer than the current age of the universe. But for a tiny black hole, the evaporation could be much faster. Hypothetical primordial black holes of sufficiently small mass might be evaporating today, possibly producing bursts of high-energy radiation. None have been confirmed. The simplest popular explanation of Hawking radiation involves pairs of virtual particles near the event horizon. Quantum uncertainty allows temporary fluctuations in fields. A particle and its partner appear. One falls into the black hole, the other escapes. The escaping particle becomes Hawking radiation, and the black hole loses mass. This picture is useful, but it is only a metaphor. The real calculation is not simply a particle pair being split at the horizon. It involves quantum fields defined in curved space-time, and the fact that different observers do not always agree on what counts as a particle. The event horizon changes the structure of the vacuum. What looks like empty space in one context can look like a bath of particles in another. The result is not a trick. It is a profound union of quantum theory, gravity, and thermodynamics. Hawking radiation means black holes have temperature. Bekenstein. Hawking entropy means black holes have entropy. Together they suggest that the horizon area counts something microscopic, even if we do not yet know exactly what. This was the beginning of black hole thermodynamics. It also led to one of the most important hints in theoretical physics. The entropy of a black hole depends on area, not volume. This idea inspired the holographic principle, the proposal that information contained in a region of space may be described by degrees of freedom on its boundary. In ordinary life, this sounds impossible. A room's contents seem to require a three-dimensional description. But black holes suggest that the maximum information in a region scales with surface area. The horizon behaves like the ultimate storage limit. This idea reaches far beyond black holes. It influences string theory, quantum gravity, and attempts to understand space-time itself. But Hawking radiation also created a crisis. If a black hole evaporates completely, what happens to the information about everything that formed it and fell into it? The radiation appears thermal. Thermal radiation is random in a particular way. It carries information about temperature, but not about the detailed identity of the object that produced it. A burning book releases heat and smoke, but in principle, the laws of quantum mechanics preserve information about the book's original state in correlations among the particles. Hawking's calculation seemed to say that a black hole erases those correlations. If true, black holes destroy information. And if information can be destroyed, quantum mechanics is incomplete. The black hole information paradox is not just a puzzle about black holes, it is a puzzle about whether the universe remembers. In quantum mechanics, the evolution of a closed system is believed to be unitary. This means that information is preserved. The present state, in principle, contains the information needed to reconstruct the past and predict the future. In practice, this may be impossible for complex systems, but the information is not fundamentally destroyed. A black hole seems to challenge this. Imagine throwing an encyclopedia into a black hole. Then throw in a piano, a comet, a cloud of hydrogen, a spaceship, a memory card, and a cup of coffee. From outside, once the black hole settles down, its external properties are reduced to mass, spin, and charge. The details are hidden behind the horizon. For a time, this seems acceptable. The information is not destroyed, it is merely inaccessible. It remains inside the black hole. But Hawking radiation changes the story. If the black hole slowly evaporates, its mass decreases. Eventually, if the process continues to completion, the black hole disappears. What remains is radiation. If that radiation is purely thermal and contains no detailed information about what fell in, then the original information has vanished from the universe. Perimeter Institute describes the paradox as the question of whether information can be retrieved from a black hole, noting that Hawking radiation seemed to imply evaporation and information loss, while later investigations suggest information may be preserved after all. This is the paradox. General relativity says information can fall behind a horizon and never return. Quantum mechanics says information cannot be destroyed. Hawking's calculation says the black hole can disappear, leaving only thermal radiation. All three statements cannot be true in their simplest forms. Something must give. One possibility is that information is truly destroyed. Hawking originally argued along these lines. Perhaps quantum mechanics must be modified. Perhaps black holes reveal that the universe is not fully unitary. But many physicists resist this conclusion because unitarity is deeply embedded in quantum theory. If information can vanish, the foundations of physics become unstable. Predictions may lose consistency. Cause and effect may become probabilistic in a more radical way than quantum mechanics already allows. Another possibility is that information escapes in Hawking radiation after all. The radiation may appear thermal at first glance, but perhaps subtle correlations encode the information. In this view, Hawking's original calculation was an approximation that missed tiny effects that become crucial over the lifetime of the black hole. This idea is now widely explored, but it raises another problem. How can information escape from behind the horizon without traveling faster than light? If nothing inside the horizon can send a signal outward, how can the outgoing radiation know what fell in? One answer is black hole complementarity. According to complementarity, no single observer sees a violation of physics. An outside observer may describe information as being absorbed and later re-emitted from near the horizon. An infalling observer may pass through the horizon and experience nothing special. The two descriptions cannot be combined into one ordinary picture, but no observer can witness a contradiction directly. This is bold, but not universally accepted. Then came the firewall paradox. A group of physicists argued that if information escapes in Hawking radiation, while quantum entanglement obeys its usual rules, then the event horizon of an old black hole may not be smooth. Instead, it may become a high-energy barrier, a firewall. An infalling observer would burn at the horizon. This would violate the equivalence principle, one of the guiding ideas behind general relativity. According to that principle, for a sufficiently large black hole, nothing locally dramatic should happen at the horizon. The firewall debate forced physicists to confront a painful choice: preserve unitarity, preserve smooth horizons, or preserve standard rules of quantum entanglement. Keeping all three appears difficult. Another proposal comes from string theory, fuzzballs. In the fuzzball picture, black holes are not empty interiors ending in singularities. Instead, each black hole microstate corresponds to a complex, horizon-sized configuration of strings and branes. There may be no traditional interior in the classical sense. Information is not lost because the black hole has structure at the horizon scale. This idea offers a way to replace the featureless black hole with a quantum object. But it remains challenging to connect fully with all aspects of observed astrophysical black holes. A different line of research comes from holography, especially the ADC-CFT correspondence. This is a mathematical relationship between certain theories of gravity in a higher dimensional space-time and quantum theories without gravity on the boundary of that space-time. In such models, black hole evaporation can be described in a way that preserves information. This has convinced many theorists that information is not destroyed. But our universe is not exactly the kind of space-time used in the simplest versions of ADC-CFT. The correspondence is powerful, but applying its lessons directly to real black holes remains a deep challenge. More recently, calculations involving quantum extremal surfaces and so-called islands have reproduced the Page curve in certain models. The Page curve describes how the entropy of Hawking radiation should rise at first and then fall if information is preserved. These calculations suggest that parts of the black hole interior may be encoded in the radiation in a surprising way. This is one of the most exciting developments in theoretical physics. Yet it is not the final answer. The models are simplified. The conceptual meaning is still debated, and a complete theory of quantum gravity remains missing. The information paradox has lasted so long because every proposed solution demands a revision of something we thought we understood. Maybe space-time is emergent. Maybe locality is approximate. Maybe horizons are not what they seem. Maybe information is encoded non-locally. Maybe black holes are telling us that the universe is holographic. The paradox is not merely about whether a diary thrown into a black hole can be reconstructed. It is about the basic architecture of reality. Does the universe keep a perfect record? Or are there places where the record ends? What happens inside a black hole? The honest answer is that we do not know. General relativity gives us mathematical descriptions, but the interior is hidden behind the event horizon. No signal can return from within. No telescope can look inside. We can infer, calculate, and simulate, but direct observation is forbidden by the very definition of the horizon. In the simplest non-rotating black hole, anything crossing the horizon moves inevitably toward the singularity. The singularity is not located in space in the usual sense. It is more like a future moment that cannot be avoided. Just as you cannot avoid tomorrow, an object inside a Schwarzschild black hole cannot avoid the singularity. This is difficult to picture because our everyday intuition separates space and time. We imagine moving inward as a choice. Inside the horizon, according to the classical theory, inward motion becomes tied to the direction of time. The singularity lies in the future of every possible path. For rotating black holes, the mathematical structure is stranger. The Kerr solution contains inner horizons, ring singularities, and possible extensions to other regions of space-time. Some mathematical interpretations suggest pathways to other universes or regions, but these are not known to be physically realistic. Inner horizons may be unstable. Infalling radiation may become infinitely amplified. Quantum effects may change the picture entirely. Science fiction often turns black holes into portals. Physics is more cautious. Wormholes are solutions to Einstein's equations, but traversable wormholes require exotic conditions not known to exist naturally. A real astrophysical black hole formed by collapse is not expected to become a safe tunnel through space. The mathematics allows many possibilities, but nature decides which ones are real. The deeper issue is the singularity. A singularity is where a theory gives an infinite answer, infinite density, infinite curvature, infinite tidal forces, but infinities in physics usually mean the model has broken down. When classical electrodynamics predicted infinities for point charges, quantum theory changed the picture. When Newtonian gravity failed near Mercury's orbit, general relativity provided a deeper theory. The black hole singularity may be a similar signpost. It points toward quantum gravity. A theory of quantum gravity would describe space-time itself in quantum terms. It would explain what happens when gravity is strong and distances are tiny. It might remove the singularity, replacing it with a bounce, a quantum core, a fuzzball, a transition to a new region, or something we have not yet imagined. But without direct access to the interior, how can such ideas be tested? One way is through the exterior. Quantum gravity may leave subtle signatures in gravitational waves, black hole shadows, or the behavior of horizons. For example, after a black hole merger, the final black hole vibrates in characteristic patterns called quasi-normal modes. In general relativity, these modes depend only on the black hole's mass and spin. Future observations may test whether real black holes ring exactly as Einstein's theory predicts. Another possible signal would be echoes after gravitational wave mergers, produced if the horizon is replaced by some quantum structure. No such echoes have been confirmed. The idea remains speculative. Black hole shadows may also test gravity. The size and shape of the shadow depend on space-time near the horizon. Current Event Horizon Telescope observations are consistent with general relativity, but future images with higher resolution may reveal more. Still, the interior remains protected. This may be a clue. Perhaps the universe senses singularities behind horizons. Roger Penrose proposed the cosmic censorship conjecture, suggesting that singularities formed by gravitational collapse are hidden from distant observers. If true, nature prevents naked singularities, singularities visible from the outside. But cosmic censorship remains unproven in full generality. The horizon hides the place where known laws fail. That is both frustrating and elegant. The universe may allow the formation of regions where physics breaks down, but it wraps them in a boundary that prevents the breakdown from contaminating the outside world. Black holes become cosmic vaults, locking away the singularity. Yet Hawking radiation complicates this again. If the black hole evaporates, the horizon shrinks. If it disappears completely, what happens to the singularity? Does quantum gravity resolve it before the end? Is there a final burst? Is there a remnant? Does the black hole transition into something else? Does space-time itself pinch off? We do not know. The end of a black hole may be the beginning of the deepest physics. A black hole can grow. It grows by accreting matter. It grows by merging with other black holes. It grows whenever energy crosses its horizon. But Hawking radiation says a black hole can also shrink. For black holes in the current universe, growth usually dominates. The cosmic microwave background fills space with radiation at about 2.7 Kelvin. A stellar mass black hole is far colder than this. It absorbs more energy from the environment than it emits through Hawking radiation. Supermassive black holes are colder still. Only in an extremely far future, after the universe has expanded and cooled, would large black holes begin to lose more energy than they gain. Then, over timescales so enormous that ordinary language fails, they would evaporate. The lifetime of a black hole scales with the cube of its mass. A black hole with the mass of the Sun would take roughly 10 to the 67 years to evaporate by Hawking radiation. That is not merely longer than human history, longer than the age of Earth, or longer than the age of stars. It is longer than the current age of the universe by more than 50 orders of magnitude. A supermassive black hole could last around 10 to the 90 years or more, depending on its mass. In the far future, after stars burn out and galaxies fade, black holes may be among the last major organized objects remaining. They would sit in a darkening cosmos, slowly leaking radiation, growing hotter as they lose mass. Near the end, the process would accelerate. As the black hole becomes smaller, its temperature rises. It radiates more strongly. The final moments, according to the simplest theory, could release a burst of high-energy particles. If primordial black holes of the right mass formed in the early universe, some might be reaching this final stage today. Searchers have looked for signatures such as gamma-ray bursts, but no confirmed evaporating primordial black hole has been detected. The death of black holes is therefore theoretical but not fantasy. It follows from combining quantum field theory with curved space-time. It may be incomplete, but it is one of the strongest clues we have that gravity, quantum mechanics, and thermodynamics are connected. Black hole evaporation also changes how we think about permanence. In classical relativity, black holes are eternal unless disturbed. Once formed, they remain. Their horizons may grow, merge, or settle, but they do not simply disappear. Quantum theory gives them mortality. The black hole, symbol of the inescapable, becomes temporary. This is a profound reversal. The universe's ultimate trap leaks. Its darkest prison glows. Its silence has a temperature. But if black holes die, the information paradox becomes unavoidable. A black hole that lasts forever can hide information forever. A black hole that evaporates must return the information, destroy it, or leave it in some remnant. Each possibility is strange. If information returns, it must be encoded in radiation that appears almost thermal. The black hole must act like an extraordinary scrambler, mixing information so thoroughly that decoding it would be practically impossible, though not forbidden in principle. If information is destroyed, quantum mechanics must change. If information remains in a remnant, that remnant must somehow store an enormous amount of information in a tiny object, raising new problems about infinite species and stability. If the black hole ends by creating a baby universe, information may leave our universe without being destroyed globally, but from our perspective it would be lost. This is another speculative possibility. Every route leads to unfamiliar territory. This is why the death of black holes matters. It is not only about the far future, it is about the present foundations of physics. If we can understand how a black hole evaporates, we may understand how space-time stores information, how quantum gravity works, and why the laws of nature are consistent. Hawking radiation is faint, but its implications are enormous. One of the strangest lessons of black holes is that information may be measured in area. In ordinary thinking, the amount of information inside a region should scale with volume. A larger box can contain more books, more particles, more arrangements. Double the volume, and you expect more storage capacity. Black holes suggest otherwise. The entropy of a black hole is proportional to the area of its event horizon, not the volume inside, the area. This means the maximum entropy or information capacity of a region is related to the surface surrounding it. This idea became one of the roots of the holographic principle. A hologram is a two-dimensional surface that encodes a three-dimensional image. The holographic principle suggests that, in quantum gravity, the information describing a volume of space may be encoded on a lower dimensional boundary. This is not just poetic language. In certain theoretical universes, the idea is mathematically precise. The most famous example is the AD-SK-CFT correspondence, proposed by Juan Maldacena in 1997. It relates a gravitational theory in a kind of space-time called anti-de Sitter space to a quantum field theory on its boundary. In this relationship, a black hole in the bulk can correspond to a thermal state in the boundary theory. This has deeply influenced modern physics. It suggests that space-time itself may not be fundamental. It may emerge from quantum information, entanglement, and boundary degrees of freedom. Gravity may be a large-scale description of something more basic. This is a radical idea. We usually imagine space as the stage on which physics happens. Particles move through space. Fields exist in space. Events occur at places in space, but black holes suggest that space may be built from deeper informational relationships. Entanglement may stitch regions together. Geometry may arise from quantum correlations. The smooth space-time of general relativity may be like the surface of water, real at large scales, but made of hidden microscopic structure. If so, a black hole is not just an object inside space-time. It is a clue to what space-time is made of. The connection between black holes and information has reshaped the language of theoretical physics. Terms once associated with computation now appear in gravity, entropy, scrambling, qubits, error correction, complexity. Black holes may be the fastest scramblers in nature, rapidly mixing information among their degrees of freedom. The Hayden Preskill thought experiment asked how quickly information thrown into an old black hole could be recovered from its Hawking radiation. Surprisingly, under certain assumptions, the answer is very quickly after a scrambling time, once enough radiation has been collected. Perimeter Institute described this as a view in which black holes can act like information mirrors. But there is a catch. Recovering the information would be unimaginably difficult in practice. The radiation is dispersed across space. The correlations are subtle. The decoding process may be computationally impossible for any realistic observer. The information may be preserved in principle, but lost for all practical purposes. This distinction matters. Physics often separates what is fundamentally possible from what is practically possible. A shattered glass does not reassemble itself, even though microscopic laws may preserve information. The information about the original glass becomes dispersed into the environment. In principle, it exists. In practice, it is unrecoverable. Black holes may be similar, but far more extreme. The black hole information paradox asks whether information is lost, even in principle. Holography suggests it is not, but the exact mechanism remains mysterious. How does the information get out? Where is it stored? What does the interior mean if the radiation already contains it? Are the interior and exterior independent, or are they two descriptions of the same quantum information? Does space-time have built-in error correction, allowing interior regions to be reconstructed from different parts of a boundary? These questions are no longer science fiction. They are active research. Black holes have become laboratories for quantum information theory, even when no physical laboratory can reproduce their gravity. They teach us that the universe may be less like a machine and more like a code. When two black holes orbit each other, they disturb space-time. At first, if they are far apart, the waves they produce are weak. The black holes slowly lose orbital energy. Their orbit shrinks. They circle faster. The waves become stronger. In the final moments, the black holes whirl around each other at incredible speeds. They merge. The horizons combine. The new black hole is distorted, vibrating violently. Then it settles down, radiating away the last disturbances as gravitational waves. This final settling is called ringdown. The ringdown is one of the cleanest tests of black hole physics. According to general relativity, the vibration frequencies of the final black hole depend only on its mass and spin. This is connected to the no-hair idea. A black hole has no mountains, no chemical composition, no surface patterns, no material crust. Disturb it, and it rings with tones determined by geometry. LIGO's first detection, GW50914, matched the predictions of general relativity. Two black holes merged, producing a final black hole and releasing gravitational waves. The signal traveled across the universe for 1.3 billion years before passing through Earth. The change in the detectors was far smaller than the width of a proton, yet it carried news of one of the most violent events in the cosmos. Gravitational waves allow us to study black holes in a way light cannot. Light comes from matter around black holes. Gravitational waves come from the motion of the black holes themselves. They are direct messengers of strong gravity. Each detection adds to a growing catalog. Some black holes are heavier than expected. Some spin in surprising ways. Some mergers may suggest complex formation histories. The population of black holes is becoming an astronomical subject in its own right. Future detectors may hear much more. Ground-based detectors can observe stellar mass black hole mergers. Space-based detectors could detect lower frequency waves from supermassive black hole binaries. Pulsar timing arrays look for the slow gravitational wave background produced by many distant supermassive black hole pairs. The universe may be humming with black hole mergers. These observations may help answer questions about galaxy evolution, stellar death, and gravity itself. But they may also probe the horizon. If black holes are exactly as general relativity predicts, merger signals should match the theory. If horizons are modified by quantum effects, there might be tiny deviations. These could appear as altered ringdown modes, echoes, or unexpected tidal behavior. So far, no confirmed deviation has overturned Einstein's theory, but the search continues. The challenge is that quantum gravity effects may be extremely small for large black holes. The event horizon of a stellar mass or supermassive black hole is huge compared with the Planck scale, where quantum gravity is expected to become strong. If the horizon is smooth, observable deviations may be tiny, yet the information paradox suggests that something subtle must happen. The black hole may look classical from the outside, while still encoding information quantum mechanically. The correction may not appear as a dramatic surface or firewall. It may be hidden in correlations too delicate to measure directly. This is frustrating, but it is also typical of deep physics. The universe often reveals its secrets indirectly. Atoms were inferred before they were imaged. Neutrinos were predicted before they were detected. Gravitational waves were calculated a century before they were observed. Black hole quantum effects may require patience on a similar scale. The sound of black hole collisions is already teaching us that the invisible can become measurable. The next question is whether the quantum structure of horizons can also be heard. The image of the black hole in M87 changed the public imagination. It showed a ring of light surrounding darkness. But the image was not a photograph in the ordinary sense. It was a reconstruction from radio waves collected by telescopes across Earth. It represented emission from hot plasma near the event horizon, shaped by gravity, motion, and relativity. The dark center is called the black hole shadow. It is larger than the event horizon itself because gravity bends light. Photons that pass too close are captured. Others orbit or are deflected. The shadow is the region on the sky from which light paths are swallowed by the black hole. The bright ring is not a solid ring. It is radiation from matter around the black hole, distorted by strong gravity. One side can appear brighter because gas moving toward us is boosted by relativistic effects. Time dilation, gravitational redshift, Doppler beaming, and lensing all contribute to what we see. NASA notes that the accretion disk can appear warped because the black hole's gravity bends space-time and forces light to follow distorted paths, producing unusual views of gas behind and beneath the black hole. The shadow is important because its size and shape test general relativity. For M87, the observed ring was consistent with a black hole of about 6.5 billion solar masses. For Sagittarius, a star, the challenge was different. Our galaxy's central black hole is much closer, but much smaller. Its surrounding gas changes on timescales of minutes, making imaging more difficult. Still, the Event Horizon Telescope produced an image of its ring-like structure. Together, these images show black holes at vastly different scales. M87's black hole is billions of solar masses. Sagittarius. A star is millions. Yet both appear consistent with the same underlying theory. This scale invariance is part of the beauty of black holes. A black hole's behavior can be described in terms of mass and spin, whether it is born from a star or sits in the center of a galaxy. The image also reminds us that black holes are not cosmic vacuum cleaners. They do not suck in everything around them. If the Sun were somehow replaced by a black hole of the same mass, Earth would continue orbiting almost as before, though without sunlight, life would not survive. Gravity at a distance depends on mass, not on whether that mass is a star or a black hole. A black hole is dangerous when you come close. Its power lies in compactness. The same mass, squeezed into a tiny region, creates extreme gravity nearby. Far away, it behaves like any other object of the same mass. This is important because black holes are often portrayed as monsters that devour the universe. In reality, they are governed by gravity like everything else. They feed only when matter loses enough angular momentum to fall inward. Gas can orbit for long periods. Stars can pass nearby and survive if they do not cross too close. Some stars are torn apart in tidal disruption events, producing bright flares as debris falls toward the black hole. The shadow is not a mouth, it is a boundary of visibility. It tells us where light paths end. Black holes do not only bend space, they bend time. In general relativity, gravity affects the rate at which time passes. Clocks deeper in a gravitational field tick more slowly relative to clocks far away. This is gravitational time dilation. It is not merely theoretical. It must be accounted for in technologies such as GPS, where satellite clocks and Earth clocks experience time differently. Near a black hole, time dilation becomes extreme. To a distant observer, an object falling toward the event horizon appears to slow down. Its light becomes redshifted, stretched to longer wavelengths. It fades. In the mathematical idealization, the object never appears to cross the horizon. It becomes frozen near the edge, dimming toward invisibility. But for the falling object, time continues normally. It crosses the horizon in finite proper time. There is no contradiction because the two perspectives measure time differently. This difference creates some of the strangeness of black holes. From outside, the horizon looks like a place where time nearly stops. From the infalling perspective, it may be just another moment. From the viewpoint of global space-time, the event horizon is a causal boundary, not a physical surface. Time also changes inside. Inside a non-rotating black hole, the radial direction becomes time-like. The singularity lies in the future. This does not mean time turns into space in a simple way, but it means the structure of possible paths changes. Avoiding the singularity becomes as impossible as avoiding the next moment. Black holes, therefore, force us to abandon the idea of time as universal. Einstein already taught us that time depends on motion and gravity. Black holes make that lesson extreme. They are machines for separating perspectives. This matters for the information paradox. An outside observer may see matter approach the horizon, heat the surrounding region, and eventually become encoded in radiation. An infalling observer may pass through the horizon carrying the information inward. Which story is true? Perhaps both, but not in a way that can be combined into a single, classical picture. Black holes challenge the assumption that reality can always be described from one all-seeing viewpoint. Physics may be consistent for every observer, yet no observer may have access to the whole story. This is deeply unsettling. The universe may not allow a complete external narrative of what happens inside a black hole. And yet science seeks such a narrative. Most known black holes are massive. Stellar mass black holes form from stars and can weigh several to dozens of solar masses, sometimes more. Supermassive black holes sit in galactic centers and weigh millions or billions of solar masses. Intermediate mass black holes may bridge the gap, though their formation and abundance remain active research topics. But theory allows black holes of many masses. In the early universe, density fluctuations might have created primordial black holes. These would not require stars. They could have formed when regions of the young universe became dense enough to collapse directly. Primordial black holes are hypothetical. But if they exist, they could open windows onto conditions fractions of a second after the Big Bang. Their mass would depend on when they formed. Earlier formation could produce smaller black holes. Later formation could produce larger ones. Small primordial black holes are especially interesting because Hawking radiation becomes stronger as mass decreases. A sufficiently small primordial black hole could have evaporated already. One with the right initial mass might be evaporating in the present era. Observing such an event would be revolutionary. It would provide direct evidence for Hawking radiation and a probe of quantum gravity. No confirmed detection has occurred. Searchers look for gamma rays, cosmic rays, and other possible signatures. Non-detections place limits on how many primordial black holes of certain masses can exist. Primordial black holes have also been proposed as dark matter candidates. Dark matter is the unseen mass that appears to shape galaxies and galaxy clusters through gravity. Most evidence suggests dark matter is not ordinary matter, but its identity remains unknown. Primordial black holes could contribute to dark matter in some mass ranges, but observations constrain many possibilities. They are not a simple solution to all dark matter. Still, they remain fascinating. A primordial black hole would be a relic from the earliest universe. It would be older than stars, older than galaxies, a fossil of density, gravity, and quantum fluctuations. If one evaporated near us, it might reveal the faint glow Hawking predicted, but the universe has not yet given us such a signal. Part 14. The question of reality. Black holes raise a philosophical question that is also scientific. What is real if it cannot be observed? The inside of a black hole cannot send information to the outside, yet general relativity describes it. Equations extend beyond the horizon. Infalling observers experience something. The interior seems physically meaningful, but in quantum gravity, the story may change. If the information inside is encoded on the horizon, or in Hawking radiation, or in a boundary theory, then the interior may not be independent in the way classical physics suggests. This does not mean the interior is imaginary. It may mean that space-time is redundant. Modern physics often contains redundancy. In electromagnetism, different mathematical potentials can describe the same physical fields. In quantum mechanics, different descriptions can encode the same state. In holography, a gravitational interior may be encoded in a lower dimensional quantum system. The black hole interior may be real in one description and emergent in another. This is difficult because human intuition evolved for ordinary objects. A stone has an inside and an outside. A room has volume and walls. A box contains things. But a black hole is not a normal container. Its boundary is causal. Its entropy scales with area. Its interior may be encoded in ways that defy ordinary spatial separation. Black holes may be telling us that space is not fundamental. Perhaps distance is not the deepest relation between things. Perhaps entanglement is deeper. Perhaps geometry emerges from quantum information like temperature emerges from molecular motion. No single molecule has a temperature, but many molecules collectively do. Maybe no single quantum degree of freedom has geometry, but many together create space-time. If this is true, then black holes are not exceptions to the universe's order. They are clues to that order. The place where physics seems to break may be the place where the next theory begins. We know black holes exist. We know this through multiple independent lines of evidence. We see X-rays from accreting stellar mass black holes. We track stars orbiting invisible compact masses. We observe gravitational lensing. We detect gravitational waves from black hole mergers. We image black hole shadows with Earth-sized telescope networks. We know general relativity describes them extremely well at large scales. The orbits near Sagittarius, a star, the gravitational waves from mergers, and the shadows observed by the Event Horizon Telescope all agree broadly with Einstein's theory. This does not prove the theory is complete, but it shows that any deeper theory must reproduce general relativity where it has been tested. We know black holes have event horizons, or at least objects behave in ways strongly consistent with horizons. The distinction matters because direct proof of an event horizon is subtle. We infer horizons from compactness, darkness, accretion behavior, gravitational waves, and the lack of surfaces. The evidence is strong, but the horizon itself is not a material object we can touch or illuminate. We know black holes can merge. Gravitational waves have made this undeniable. We know supermassive black holes live in galactic centers. The Milky Way has one. M87 has one. Many galaxies appear to have them. Their growth and feedback shape cosmic history. We know that classical black holes are simple from the outside. Mass and spin dominate their description. We know Hawking radiation is a powerful theoretical prediction. It follows from quantum field theory in curved spacetime. It gives black holes temperature and entropy. It implies evaporation. But it has not been directly detected from an astrophysical black hole. We know the information paradox remains unresolved. There has been major progress, especially through holography and page curve calculations in simplified models. But a complete, experimentally confirmed theory of quantum gravity does not yet exist. This is the current state of the mystery. Black holes are real enough to photograph and hear, but strange enough to threaten the foundations of physics. We do not know what happens at the singularity. General relativity predicts singularities under broad conditions, but singularities signal the breakdown of the theory. Quantum gravity is expected to change the picture, but how remains unknown. We do not know the exact microscopic origin of black hole entropy. The Bekenstein-Hawking formula tells us how much entropy a black hole has. Some theories can count microstates for certain idealized black holes. But a complete description for all real astrophysical black holes remains part of the larger quantum gravity problem. We do not know exactly how information escapes, if it escapes. Many physicists believe information is preserved. Holographic models support this. But the mechanism in our universe is still debated. We do not know whether firewalls exist. If they do, the horizon is not smooth for an infalling observer. If they do not, Something else must resolve the entanglement puzzle. We do not know whether fuzzballs describe real black holes. They offer a possible string-theoretic solution, but their relation to ordinary black holes remains under investigation. We do not know whether primordial black holes exist. They could illuminate the early universe, dark matter, and Hawking radiation. But none have been confirmed. We do not know how the first supermassive black holes grew so quickly. Early quasars suggest rapid growth in the young universe. The seeds and feeding mechanisms remain active research topics. We do not know whether spacetime is fundamental. Black holes suggest it may be emergent from quantum information. But this is not yet a completed theory. The mystery of black holes is therefore not one mystery. It is a network of mysteries connected by gravity, quantum theory, thermodynamics, information, and cosmic evolution. Stephen Hawking's discovery changed the meaning of black holes. Before Hawking radiation, black holes were endpoints. Matter could fall in. The horizon could grow. The black hole could persist. It was a one-way object. After Hawking, black holes became dynamic quantum systems. They had temperature. They had entropy. They could evaporate. They could die. And in dying, they forced physics to confront whether information is fundamental. Hawking radiation is not just another kind of cosmic glow. It is a message from the border between known theories. It uses general relativity to define the black hole space-time. It uses quantum field theory to describe particles and vacuum fluctuations. It uses thermodynamics to interpret temperature and entropy. It points toward quantum gravity because it leaves behind questions no current theory fully answers. Few ideas have done so much with so little light. The radiation from a large black hole is so faint that we may never directly detect it from ordinary astrophysical black holes. Yet, the theoretical glow illuminates the deepest problems in physics. This is Hawking's paradoxical legacy. He made black holes darker and brighter at the same time. Darker because they became more mysterious. Brighter because they became windows into the laws beneath reality. Imagine the universe in the far future. The bright age of stars has ended. New stars no longer form in great numbers. Existing stars have burned out. White dwarfs cool, neutron stars fade. Galaxies drift apart as cosmic expansion continues. The universe becomes darker, colder, emptier. But black holes remain. They are the last furnaces of gravity, the remnants of stars and galaxies, the dark archives of cosmic history. For unimaginable durations, they sit almost silently. Then, slowly, Hawking radiation drains them. The smallest evaporate first. Larger ones last longer. Supermassive black holes endure beyond almost every other structure. Eventually, even they begin to shrink. The black hole era gives way to radiation. If Hawking's prediction is correct, the universe's darkest objects end as faint heat. The final black holes vanish into particles, leaving no horizon behind. But what remains in those particles? Randomness? Information? A hidden code? The answer determines whether the universe remembers its past. Black holes are often described as places where physics ends. But for human beings, they are also places where imagination begins. We cannot visit them safely. We cannot see inside them. We cannot reproduce them in laboratories. Yet we have learned their masses, mapped their surroundings, heard their collisions, and photographed their shadows. This is one of the great achievements of science. We take signals from the sky, radio waves, X-rays, infrared light, gravitational waves. We compare them with equations written on Earth. We build instruments across continents. We synchronize atomic clocks. We simulate plasma and space-time on supercomputers. We argue over paradoxes and refine theories. Slowly, the invisible becomes known. And still, black holes resist completion. They remind us that knowledge has edges, not failures, edges. An edge is where a map becomes unfinished. It is where new exploration begins. The event horizon is a physical edge in space-time. The singularity is an edge of classical theory. The information paradox is an edge of quantum understanding. Hawking radiation is an edge where gravity, heat, and quantum fields meet. Black holes are boundaries in every sense. They are where stars end, where light ends, where time changes character, where theories collide, where certainty gives way to possibility. A black hole is simple: mass, spin, horizon. A black hole is complex: entropy, radiation, information, quantum gravity. A black hole is dark. Nothing inside the horizon can send light to the outside. A black hole is luminous. Matter around it can outshine galaxies. A black hole is silent. Then it merges and space-time rings. A black hole is a prison. Then Hawking radiation suggests it slowly leaks away. A black hole is an ending. Then it becomes a beginning. The mystery of black holes is not only that they exist, it is that they force the universe to reveal contradictions in our deepest ideas. They show us that gravity is geometry, but not only geometry. They show us that empty space is not empty. They show us that information may be as physical as energy. They show us that the boundary of a region may contain the secret of everything inside. And perhaps most importantly, they show us that darkness is not the same as nothingness. The darkness of a black hole is full of structure. It has a boundary, a temperature, an entropy, a history. It can spin, it can merge, it can ring, it can evaporate, it can challenge the laws that describe it. At the edge of a black hole, the universe becomes both a place and a question. What is space? What is time? Can information be destroyed? Does the universe remember? What lies beyond the theories we know? For now, the answers remain incomplete. But the search continues. Every star orbiting the Milky Way's center, every gravitational wave passing through Earth, every sharpened image of a black hole shadow, every equation that tries to unite relativity and quantum mechanics brings us closer. Black holes are not empty holes in the sky. They are the universe's deepest riddles. And at their edges, where light fails and time bends, physics listens for a whisper. A faint glow, a quantum trace, Hawking radiation, the smallest signal from the greatest darkness. And perhaps, hidden inside that almost impossible light, the secret of reality itself.